For matrices whose inverse doesn't exist, there is something called a pseudo-inverse of a matrix. So for example, let's say I have a matrix X and it is not a square matrix. Then for this matrix I can define a pseudo-inverse. Okay. And the notation that we'll use here is let's say this is plus, okay, the superscript plus. So what that means is that if I take X and I multiply it with this pseudo inverse, okay, and multiply the whole thing again with X, okay, I will get X back. So in some sense this is acting like an identity matrix, but it need not be an identity matrix. And for certain types of matrices there's a very easy way to compute this pseudo inverse. Okay. This pseudo inverse is equal to X. Okay, I'm not making it bold, but it is bold. Okay, and X. This is the conjugate transpose. This is conjugate transpose. What that means is you are taking the transpose, and if it is a complex, if there are any complex values, you will take the negative of the imaginary part. Okay. And this has to be invertible. The conjugate transpose times X has to be invertible, and so we'll take the inverse of that, and then we will take the conjugate transpose. So this is the definition, and with this we can almost make it act like a inverse of X. And here it does not matter if the original X is invertible or not. Now keep in mind that for this to be invertible, right, so, and this is going to be a square matrix, that keep that in mind. Why it is going to be a square matrix? Whatever is your dimension of X, so let's say it is m cross n, right, then because X H is the conjugate transpose, so because of the transpose, its dimensions are going to be n cross m. So when you multiply this together, right, what you will get is n cross m times m cross n, so you will get an n cross n matrix, right? And that matrix, if its inverse exists, let's say n is smaller than m, then in that case we can take the inverse and multiply it with again X conjugate transpose, and that will give us the pseudo inverse of the matrix X. Another important concept in matrices is its Eigen decomposition. So let's say we have a matrix A, okay, and we have a vector V, right? So if we can multiply this matrix A with its vector V, and we get some, so this is also bold, right, and we get lambda times V back. Okay. So let's say this is n cross n and this is n cross 1. So when you multiply the two together, you will get something which is n cross 1, and this is already n cross 1, right? So the dimensions check out, and this is a scalar. Then V is an eigenvector of A, and lambda is an eigenvalue of A. Okay, so keep in mind that I will actually use a subscript I here, because the pairing of lambda and V is matched in some way. So for example, if you have an n cross n matrix, it can have at most n non-zero eigenvalues, eigenvalues, right? And for each of those eigenvalues, there will be a different eigenvector. And here we assume that this eigenvector is a unit vector. V is a unit vector. What is a unit vector? If I take the square of each of its dimensions and add them up, it will add up to 1. Okay. Alright. So we can arrange all the eigenvectors into a matrix Q, and what we will get is you can decompose this matrix, you can factorize this matrix as a product of Q, this matrix Q, and a matrix lambda and a matrix Q inverse. So what is Q? Q is basically an arrangement of all the VI's, right? So it is V1, V2, V3. Now all these are column vectors. Okay, arranged as a matrix. And what is lambda? It is a diagonal matrix of all the eigenvalues, sorry, diagonal matrix. This diagonal matrix is such that you have lambda 1, lambda 2, all the way up to lambda n in the diagonal, and then rest of it is 0. Okay, so usually the way to arrange these eigenvalues is in a decreasing manner. So the highest eigenvalue is lambda 1, the next highest is lambda 2, and so forth up to lambda n. So if any of these lambdas is 0, so let's say lambda n is 0, then it is going to be a rank deficient matrix. For a full rank matrix, all lambdas have to be non-zero. Okay, so this becomes important in finding out whether two variables or if you have n variables defining a particular data set, right, then are those variables independent of each other? If some variable is a linear combination of other variables, then they are not independent. There's some redundancy in that data, and then what you will get is some of the eigenvalues, you will get them to be 0. Okay. These eigenvalues, they also basically they kind of capture the mode of variations in the data, so this will become important later on. Okay, so just keep this definition in mind. क्या चाहिए? The last concept that we'll talk about in this module are tensors. Tensors are generalization over matrices. So let's start with a scalar, right? So you have scalar alpha, this belongs to R, and then you have a vector x, okay, it belongs to R to the power n, okay, or n cross 1, and then you have a matrix which is, let's say, A, it may belong to R to the power m cross n, right? And then you may have a tensor T, okay, which may belong to R to the power, it may have more than 2 dimensions, so it may have m cross n cross p cross pq, something like that, right? So it may have several dimensions. It may be a 4-dimensional tensor or a 3-dimensional tensor. Now so just like for matrices, we had defined transpose where the m and n rows and columns get exchanged. Here, if we have to define a transpose for a tensor, then we don't know which of these dimensions get exchanged with what. So when we define that transpose, especially in programming, when we use some tensor libraries in machine learning, then we will have to give the order of the permutation of the dimensions, right? So we may want to say that find the transpose of T, okay? So now that's it, some R is equal to transpose of T, but then we also want to give an order. So let's say this is 0th dimension, 1 dimension, 2 and 3 dimension. So the order could be 3, 1, 2, 0, right? So this order of permutation of dimensions has to be defined. So why are these tensors important? Sometimes the data itself is not simply a vector, but it is in a two-dimensional array, or I hesitate to call it a matrix. It's a two-dimensional array. So if the data itself is a two-dimensional array and you have several such data points, then you need a third dimension. Sometimes you even need a fourth dimension if the data is a three-dimensional tensor itself. So it's important to keep in mind that matrices or two-dimensional arrays can be generalized to n-dimensional arrays or tensors.